So you're sitting there all by yourself, and at the next table you notice there's Freeman Dyson, there's Armand Borel, and they're having their own lunch very nicely and quietly, but then they start arguing. And Borel says, look, give me a prime. Dyson says, 2 to the 31 minus 1. Armand says, no, I want the actual digits. Don't give me any exponents. I want to actually write down the prime. So Freeman Dyson says, all right, here's a prime. 111, 111, 111, 111, 111, 19 times, 19 ones. There's a prime for you. And Borel says, it's getting there, but I need at least 20 digits. And they can't be all ones. And they think for a minute, and there's a bit of silence. And you cough quietly, and you say, gentlemen, I think I can help you. Here's a prime for you. 20 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That decimal number is a prime, gentlemen. Borel closes his eyes and thinks for a minute. He says, could be. Looks like you're right. And Freeman Dyson says, well, congratulations, young man. Do you know any other primes like that? And you say, well, you can look more generally at what you get if you go out up to n. So let's write down the decimal number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12. Go all the way up to n. And we're going to string all these digits together. And then we go down, n minus 1, n minus 2, down to 4, 3, 2, 1. So that's a number, rather large number, if n is large, and it depends on n.
Can I ask a quick question?
Yes.
Obviously, 11 counts as 1, 1, and 12 counts as 1, 2.
Exactly.
And when we go back down the slide, will 12 become 2, 1?
No, 12 it stays at 1, 2. So we read the numbers just as they are on the blackboard, and they go up and then they go down. So it goes, the last would be 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, stop. And so you can say, when is that a prime?
For what n?
For what n is that a prime? Well, 10 works. N equals 10 gives a prime. And Borel says, and what's the next prime? You say you have to go out to n equals 2, 4, 4, 6 to get another prime. And beyond that, we don't know. So this is a pretty large prime, and we don't know any more. So, Brady, it's a story you can tell at parties. And, of course, we would like another few terms, so we can... The sequence is not yet, the sequence 10, 2, 4, 4, 6, is not yet in the OAIS because we only have 2 terms. It's too short.
How many terms does it have to have before you'll put it in the online encyclopedia?
There are some sequences where 1 term is enough that are really, really important. But for something like this, more than 6 digits, if you can. I mean, a couple more terms would be perfect. Officially 5 terms, but we'll certainly make exceptions if the terms are big.
Neil, that prime that has n equals 2, 4, 4, 6 must be a huge number.
It's a huge number.
Should we believe there are an infinite number of n's this will work for?
Yes, absolutely. You can do the math. You can look at the probability that in a number like this is a prime, and the probability is 1 over whatever it is, and that summation diverges. So we expect with confidence that there'll be infinitely many. It gets harder as the numbers get bigger, and presumably the man who found 2446 took it some distance further, but I don't think anyone has seriously looked into this. I call this one a memorable prime, the one with 10 in the middle. I'm not finished. I have another segment. This is the most wanted prime in the world. So you saw the primes we just did. You start at 1, and you go 1, 2, up to n, and then you go down n minus 1 down to 1. But surely the more logical question is, what if you start at 1 and go up to n and stop? So let's do it. 1, that's not a prime. 1, 2, that's certainly not a prime. 1, 2, 3, well, it's not a prime, it's 3 times 41. 1, 2, 3, 4, obviously if n, we're going to go up to n and stop. And if n is even, there's not a chance. If n is 5, there's no chance that it's a prime. And if the sum of the digits is 3, there's no chance it's a prime. 6, that's most definitely not a prime. What about 1, 2, 3, 4, 5, 6, 7? That looks like it might be a prime. Well, it's not. It's divisible by 127. Sorry. So we keep going. We want a prime. We definitely want a prime. This really is, it's sort of the most natural prime for anyone with 10 fingers. 10, 11. 11 doesn't work either. 12, 13. So let me talk about 13 for a minute. So go 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 0, 1, 1, 1, 2, 1, 3. These are just the digits of this number, okay? And we say, all right, now that really looks like it's a prime. It's not. It's divisible by 113. Sorry. Well, all right, so you keep going up to n. And every time you get to n, you stop and think. And when n gets large, you have to think quite a while before you can tell whether it's a prime or not. So various people helped me with this, and then I asked the people who run the GIMP, the Great Internet Mersenne Prime Search, who've been looking for Mersenne primes, because this is exactly their kind of problem. And they took it up. A group of them worked on it for quite a while. And they got up to n equal to 340,000. And they still hadn't found a prime. And I'm afraid they've given up. Because, do the math, look at the chance that a number like this, up to n, is a prime. Roughly it looks like there's a 50-50 chance. By the time you get up to 1 million, you should have hit a prime. So I would like to encourage the world to keep going and find this missing prime.
This episode has been brought to you by Climeworks. We're all pretty conscious of the amount of carbon dioxide being put into the atmosphere. Climeworks is an innovative company doing something about it by literally capturing CO2 from the air itself. It's then reused by other businesses or permanently stored underground, basically as mineralized stone. Here's some of their kit in action. It's in Iceland. And you can be a part of it. They have various plans where you pay monthly to have carbon dioxide captured in your name. You will know exactly how much CO2 was removed from the atmosphere directly because of you. Or if not you, this could be a great present to give that person in your life who doesn't want another pair of socks or endless boxes of chocolates, but they would like to know that they're part of a planet-saving mission. Anyway, to find out more, go to gift.climeworks.com/numberphile. The website's actually really good for showing how it all works. There's the link on the screen, and of course there will be a link in the video description. Our thanks to Climeworks.